In this unit, we have already used the equation delta G equals delta G naught plus RT log Q, with help from delta G equals negative NFE, to derive the Nernst equation. And there it is. In units on thermodynamics, it is often shown that at equilibrium, where delta G equals 0 and Q equals K, the same equation will yield the results delta G naught is equal to negative RT log K, and written in a different way, K is equal to e to the power negative delta G naught over RT. These are two versions of a single equation that relates the standard change in Gibbs free energy to the value of the equilibrium constant. We now add to this, using once again the fact that delta G naught equals negative NF E naught. We now turn delta G naught equals negative RT log K into this. Negative NF E naught is equal to negative RT log K, which we can simplify into that right there. E naught is equal to RT over NF log K, where R is 8.314 joules per mole Kelvin, T is the temperature in kelvins, N is the number of moles of electrons, F is Faraday's constant, 96,485 coulombs per mole of electrons. Similarly, we can change that equation into this one, and those. These four equations represent a very powerful equation toolbox. Armed with these equations, if we know any one of delta G naught, E naught, or K, we can determine the other two. So let's do that. Determine the value of the equilibrium constant at 25 degrees Celsius for this reaction. The relevant equations from the table are the reduction of iron 2 and the reduction of the silver ion. We see from the equation that the reduction of iron 2 needs to be flipped into an oxidation, because clearly in the equation at the top of the screen, iron's being oxidized. When we flip one of the reduction forms of the equation to the oxidation form, we also need to flip the sign of the reduction potential. E naught for this cell is going to be not negative 0.44, but rather positive 0.44 plus 0.8, which is 1.24 volts. This tells us that this reaction is thermodynamically favorable. That's what TF stands for, or spontaneous. And if we use one of the equations from our equation toolbox, we can figure out what the value of the equilibrium constant is. N, in this case, clearly is going to be 2 electrons. If we look at the equation here at the top of the screen, hopefully you can see that there are 2 moles of electrons that are going to be transferred. F is Faraday's constant. We just calculated E naught to be 1.24 volts. R is going to be 8.314, and the temperature in Kelvin is going to be 298. We have e to this power, which is e to the positive 96.58 power. This is obviously going to be a rather large number, and even one significant figure might be iffy. But if we round just to 1, that's the value we get. What does this tell us? Well, this tells us that equilibrium lies way to the right. We have no idea how long this reaction will take to reach equilibrium, but when it does, products are way favored. That's how you relate delta G naught with E naught with the equilibrium constant K.